So the status of our story right now is that for the real numbers, we have constructed the actual numbers and we have talked about arithmetic. There is one more issue that we have to deal with, and that is ordering the real numbers. And we order it with the relation less than. So the relation less than tells us which real numbers come before which other real numbers. So we're going to take a multi-step process to figure out what the real definition of less than is. And I'm going to do it in a way that we make mistakes, but make mistakes that really enlighten us as to the issues related to the definition. If I went right to the proper definition, it would sound kind of weird. So I wanted to tell you why we get there. So we're going to take a first guess at the definition of less than. We're going to look at a troubling example of x and y with x less than y that shows us why that first definition isn't so great. We're going to take a second guess at the definition of less than. We're going to find another troubling example that makes our definition not so great. And then finally, we're going to get the real definition of the order relation. That's going to sound weird if this was the first thing we heard, but given the examples that we had before, will hopefully make sense. All right, so let x be represented by the Cauchy sequence x1, x2, x3. So again, that Cauchy sequence in there, that is a representative Cauchy sequence of the number, and then the square brackets indicate that the actual real number x is the equivalence class of that Cauchy sequences. So there's lots of Cauchy sequences in there. And y is the real number represented by the Cauchy sequence y1, y2, y3, etc. And we want to ask ourselves, what should be the rule for when x is less than y? Well, probably the first rule that would occur to you is that x is less than y precisely when each of the xn's is less than each of the yn's for all n in the natural numbers. Right? It should be that the terms that you have in the Cauchy sequence for x should be less than the terms you have for the Cauchy sequence for y. Well, yeah, I don't know how to tell you. This definition does not work, and let me show you why. So here are two real numbers. One is represented by 2 plus 3 over n, and the other is represented by 3 minus 2 over n. And so if you look at those Cauchy sequences and ask yourself which one represents the bigger number, well, x represents the number 2, y is the number 3, and so it should be the case, based on our experience with numbers, that x is less than y. However, if you look at the first few terms of the sequence in x and the first few terms of the sequence in y, the first few terms of x are larger than the terms of y. 5 is bigger than 1, 3.5 is bigger than 2, 3 is bigger than 7 over 3. So that does not satisfy the definition that we had there. So x is less than y, but it doesn't follow our rule. So that's not so great. But here's the question. I mean, certainly at some point we got to have 2 plus 3 over n less than 3 minus 2 over n. So let's solve this inequality and just see when that happens. Let's see. What we're going to solve for n, I'll show you the result is n greater than 5. So once you get past the fifth one, all the terms do match up, where all the terms in x are less than all the terms in y. So maybe the definition, here's our second guess, x is less than y precisely when there exists some natural number big N such that once you get past that big N, once little n is bigger than big N, then xn is less than yn. And that seems like a much better definition. And I agree, it is a much better definition, still doesn't work. Because here is a situation where we have x being represented by the Cauchy sequence 1 minus 1 over n, y is being represented by the sequence 1 plus 1 over n, and, well, which is bigger? According to our rule, we have 1 minus 1 over n is always less than 1 plus 1 over n, so x should be less than y, according to our rule. However, x is the number 1 because 1 minus 1 over n converges to 1. Y is also 1 because 1 plus 1 over n also converges to 1. So it is not true that x is less than y. It is in fact true that x is equal to y. Well, no, there's no reason to cry. We're okay. So we're going to put together the lessons of our failed attempts. Failure is going to be our helper here. And then we'll get the following definition that this one will definitely work. This time for sure. So let x and y be real numbers where x is represented by the Cauchy sequence x1, x2, x3, etc. Y is represented by the sequence y1, y2, y3, etc. Then x is less than y precisely when, first of all, x is not equal to y. We're not falling into that trap again. And there exists some natural number big N such that xn is less than yn for all n greater than big N. All right, so now that you have a good idea of what the definition of our order relation is, go ahead and click the link below to see what the in-class activities are going to be like.